Right now, inside the world's most advanced AI data centers, there is water being pumped continuously right next to raw silicon chips that are running, hot enough to literally cook a meal.
Oh, absolutely. It's incredibly intense.
Right. And we are talking about tens of thousands of GPUs packed into these impossibly dense architectures, like one microscopic clog in a coolant line or just one drop of condensation from a sudden shift in the room's humidity.
And boom, millions of dollars of hardware just instantly turns into useless melted slag.
Exactly. Melted slag. That is the physical, high-stakes reality of cloud computing today. So it really makes you wonder, how do the engineers running these hyperscale facilities actually manage that kind of knife-edge operation without losing their minds?
Well, they do it by fundamentally changing how we think about the relationship between software and bare metal.
Right.
I mean, the days of just racking a server, plugging in an Ethernet cable and hoping the air conditioning holds up, those days are completely over.
Yeah, long gone.
Yeah, sheer density of modern workloads has forced an evolutionary leap in infrastructure management.
And that evolutionary leap is exactly what we are pulling apart today on this deep dive, because we are looking at a document that serves as the literal blueprint for how these modern high-intensity AI data centers are built, managed, scaled, and, kept from catching fire.
Right, which is no small feat.
For sure. Specifically, we have our hands on the April 2026 release of the SuperCloud Composer Introduction User Guide.
Right, that's release 3.12.0 from Supermicro.
Yeah, 3.12.0. And I'll be honest, it is an incredibly dense 500-plus page technical manual. But if you look past the raw schematics, it tells this really fascinating story about survival at the very edge of physical computing limits.
It absolutely does. I mean, SuperCloud Composer, or SCC as they call it, is essentially the operating system for the physical data center itself.
The OS for the building, basically.
Exactly. And to understand why a piece of software like this even had to be created, you have to look at this staggering statistic that the manual cites right in its introduction.
Oh, right, the waste stat.
Yeah. In traditional IT data centers, resources are often underutilized at rates of 45%.
Wow.
And overall operating efficiency hovers right around just 50%.
Wait, so if I'm running a hyperscale cloud, I'm effectively throwing millions of dollars into a furnace just to power idling silicon.
Pretty much.
I mean, imagine running a massive state-of-the-art manufacturing plant, right? You've got the best equipment money can buy. You're paying a premium for industrial electricity.
Right.
But when you walk the floor, half the machines are just spinning their wheels, producing absolutely nothing, yet you are paying the utility bill for every single one of them.
See, in any other industry, that level of waste would lead to immediate bankruptcy.
Yeah, you'd be shut down in a month.
Exactly.
Yeah.
But for a long time, the global data center industry just accepted that as, standard operating procedure.
Just the cost of doing business.
Right. But when you factor in the skyrocketing costs of PUE, that's power usage effectiveness, plus the huge premium on physical real estate, and the exponential climb in human manpower rates.
It just breaks down.
Yeah, that old way of doing things became mathematically unsustainable. I mean, you cannot survive a 45% waste margin when a single rack of AI servers draws a quarter of a megawatt.
A quarter of a megawatt for one rack. That's just wild. Which brings us to our core mission today. We are going to extract the secrets of how these massive AI-driven clouds actually operate in 2026.
We're tracing the whole life cycle.
Exactly. We'll start with the foundational philosophy, this idea of composable infrastructure that aims to, kill that 45% waste.
Right.
From there, we'll look at the actual physical architecture, how they scale from a single node all the way up to hundreds of racks. Then we get into the massive generative AI upgrades in this 3.12.0 release before plunging into the really fascinating, highly pressurized world of extreme liquid cooling.
That's where the plumbing comes in.
Oh, yeah. And finally, we'll map out the network's nervous system and the administrative backbone that prevents, say, a rogue command from taking down the entire grid.
It's a totally comprehensive ecosystem.
Ah.
But I think let's start at the root of the problem. That massive underutilization stems from what the Supermicro documentation calls the traditional IT paradigm.
Right, the broken paradigm. I feel like we've all lived through it.
Yeah.
You need to spin up a new service, so you order a physical server.
Yep.
That 2U metal box arrives, and it has a fixed, immutable ratio of resources. Like it has 2 CPUs, maybe a terabyte of RAM, and 10 NVMe drives. It is a sealed ecosystem.
And that fixed ratio, that is the fatal flaw. because workloads are almost never perfectly balanced.
Give me an example of that.
Sure, let's trace an actual operational scenario. Say you have an enterprise database application. It requires massive amounts of high-speed storage to cache queries, right?
Okay, heavy storage needs.
But the actual compute processing required is relatively light. So you load it onto this traditional server. Well, within a month, your storage drives are at 95% capacity.
So the box is officially full.
From a storage perspective, yes.
But the CPUs in that exact same box are barely ticking over at, what, 5% utilization?
Exactly. They're just sitting there trapped behind the metal chassis.
Wow. So you have all this dark compute power, but you can't easily hand that leftover 95% of CPU capacity to another server across the room that happens to be rendering a 3D animation and desperately needs more processing power.
No, you can't. The resources are completely marooned. Multiply that isolated inefficiency across 50,000 servers in a hyperscale facility, and, well, you arrive at that catastrophic 50% operating efficiency failure.
So the traditional model is basically like buying a pre-built, glued-together toy spaceship.
Glued together.
Yeah, like Legos. If your business suddenly needs a submarine, you can't reuse the parts because it's glued. You have to go buy a whole new toy.
That's actually a great way to picture it.
Supermicro's fundamental solution to this is what they call composable disaggregated infrastructure, or CDI. And this completely changes the physical reality of the hardware.
It really does.
Instead of glued together spaceships, CDI means you just have massive, separate bins of raw materials.
Right. The glossary in the source text explicitly defines this. Disaggregated infrastructure means that the core components, so the storage, the network, the compute, and the GPU accelerators, are physically separated into their own dedicated resource pools.
Okay.
And then they are logically assembled during a system's provisioning phase.
So I have a rack over here that is nothing but CPUs, a rack over there that is nothing but flash storage, and SCC is like the master builder.
Exactly. A software workload comes in, looks at the available resources and says, I need exactly 20 cores of compute and 50 terabytes of flash.
And then what?
Well, SEC reaches into their respective bins, snaps those logical pieces together over the high-speed network fabric, and presents it to the application as if it were a single physical server.
That is so cool.
And the beauty of this composable cloud management platform is the ephemeral nature of it.
Ephemeral. How so?
Well, when that specific workload finishes its task, say 3 hours later, SEC instantly breaks the pieces apart.
Oh, I see.
It throws those cores and terabytes back into the communal pools, ready for the next workload. The entire goal is maximizing the return on investment of every single component. You push utilization from 50% up to 80 or 90%.
That makes total sense. Let's ground this in the hardware the manual describes, though. When we talk about these isolated pools, the glossary highlights something called a JBOF. Just a bunch of flash.
Yeah, it is a wonderfully blunt acronym.
Very literal.
Right, but it represents an incredibly dense piece of engineering. A JBOF is a storage enclosure that houses a massive pool of NVMe drives.
Non-volatile memory express.
Correct. We aren't talking about the old SATA or SAS drives spinning magnetic platters, or even the older SSDs that get bottlenecked by legacy storage controllers.
Right, because NVMe devices connect directly to the PCI Express interfaces of the motherboard. They speak directly to the PCIe bus.
Exactly. And the text notes that typically 4 PCIe lanes are allocated per disk. To put that into perspective, the performance for just one single PCIe 3.0 lane is 1 gigabit per second.
Wait, per lane?
Per lane. So when you aggregate 4 lanes across 24 drives in a single chassis, the throughput is just staggering. You have a box that is just pure, unadulterated read and write speed.
Okay, but here is the architectural friction, right? If I have a JBOF sitting in rack A and a compute node sitting 50 feet away in rack D, how does the compute node talk to that storage without hitting a massive network bottleneck?
That's the big question.
Because if the network is slow, disaggregation completely falls apart. You're just waiting on cables.
That is where the protocol NVBOF becomes critical.
NVM over fabrics.
Yes. This protocol allows the disaggregation of those ultra-fast drives across a high-speed network. It basically encapsulates the NVMe commands and pushes them across the Ethernet or InfiniBand fabric so efficiently that the compute node in rack D actually thinks the hard drives in rack A are plugged directly into its own local PCIe slot.
Wow. So it tricks it.
Exactly. The latency overhead is virtually negligible.
And managing all of this chaos, I mean, Tens of thousands of drives, thousands of CPUs, all talking across the fabric. That's SuperCloud Composer's job. The manual describes it as providing a single pane of glass unified dashboard.
Right, and single pane of glass is not just a marketing term here. It's a critical operational necessity.
Why is that?
Because without it, the manpower cost to run a composable infrastructure would just negate all the hardware savings.
Oh, I see. You'd need too many people turning knobs.
Exactly. Before this kind of unified multi-tiered management, a data center operative provisioning a new cluster would have to log into a Cisco interface to configure the network switches, then go to a completely different NetApp interface to provision the storage volumes.
Oh, that sounds awful.
Then an IPMI console to set the bare metal compute parameters, and yet another interface to monitor the power draw. It was just a fragmented nightmare.
So how does SCC actually unify heterogeneous hardware? Like if I have a Supermicro server, an Arista network switch, and a Schneider electric power unit, they don't natively speak the same language.
No, they don't. The text mentions SCC heavily relies on the Redfish northbound API message bus.
Redfish, okay.
Yeah, the Redfish API is basically the Rosetta Stone of the modern data center.
I love that analogy.
The glossary defines it as using RESTful APIs to manage servers, storage, networking, and converged infrastructure. By standardizing on this industry-wide protocol, SEC acts as a universal translator.
Okay, so it talks to everything.
Right. It queries the Redfish interface of every component in the data center, aggregates all that telemetry, and presents it in that unified dashboard. This means the infrastructure is inherently software-defined.
So you can script it.
Exactly. It allows administrators to automate massive deployments from the core data center all the way out to edge computing sites, all through API calls rather than manual configuration.
But the manual is also very pragmatic, which I appreciate. It notes that this transition to composable disaggregated infrastructure doesn't require a forklift upgrade.
Right. You don't have to replace everything at once.
Yeah, it supports a hybrid approach.
Which is vital for any enterprise. I mean, you can't just whip out your legacy multi-generation Supermicro servers overnight.
No, the business would halt.
Right. SCC allows operations teams to manage their traditional fixed ratio servers right alongside their cutting-edge disaggregated resource pools. It gives organizations a phased evolutionary path to modernize their data centers without disrupting ongoing revenue-generating workloads.
Okay, so we've established the why. The traditional model is inefficient, CDI breaks the resources into pools, and SCC uses Redfish to manage the orchestration. But I want to move out of the logical philosophy and into the physical reality.
Let's do it.
Because if I am standing on the data center floor looking down a hot aisle, how is all of this actually organized? Section 2 of our deep dive looks at architecture and scale. The manual lays out a very strict hierarchy.
It does. It builds from the microscopic to the macroscopic. So the foundational atomic unit is the node. This could be a compute node, a storage node, or a network node.
Okay, node is the base. And you don't just bolt a node to a rack. Multiple nodes slide into a drawer.
Right. The drawer is a chassis, a metal enclosure, that basically shares power and cooling resources among the nodes inside it.
Got it.
Then you stack multiple drawers vertically inside a standard 19-inch or 21-inch rack. And finally, the highest level of physical grouping is the pod.
The pod.
Yeah, a pod is a physical collection of multiple racks that are networked together into a cohesive fabric.
Node, drawer, rack, pod. It makes logical sense. But as you scale up, the management overhead becomes terrifying.
Oh, absolutely.
Because if I have a pod consisting of, say, 20 racks, and each rack has a dozen drawers, and each drawer has 4 nodes, I am suddenly dealing with thousands of independent endpoints. How do you manage an entire pod without the telemetry data just overwhelming the administrators?
Well, you abstract the complexity using a pod manager.
Pod M, okay?
The text specifically highlights that SCC's rack-level management software leverages the Intel SWPM framework.
SWPM.
Yeah, it stands for Software Pod Manager. This framework is what provides the specific scale and efficiency required for cloud operators to pool and provision resources from day one across the entire pod simultaneously.
So you aren't doing this one by one.
Exactly. You aren't individually clicking into node number 4302 to check its CPU temperature. You are interfacing with the Intel SWPM framework. It aggregates the health and resource availability of the entire pod into a single data stream for SCC to digest.
I see the logic, but doesn't that create a massive bottleneck at the management plane?
It can, if you aren't careful.
Here is where it gets really interesting and honestly a bit concerning from a systems architecture standpoint. SEC itself is just software, right?
Yeah.
It runs on a virtual machine. If I'm asking this one virtual machine to ingest telemetry data, I mean power, temperature, network traffic, storage IOPS, from thousands of disaggregated components every single second, how does the SEC virtual machine not just completely lock up?
That is the ultimate test of management software at scale. And the SEC virtual machine sizing guidance in the documentation addresses this head-on.
Okay, good.
Because SEC isn't some lightweight monitoring agent. It is a heavy, enterprise-grade orchestration engine, and the hardware requirements for the VM reflect that intensity.
Let's trace these specs because they are eye-opening. Even for a single master node setup, just the core engine, the virtual machine requires 16 to 24 CPU cores.
That's a lot for a VM.
Yeah, and it mandates 64 to 80 gigabytes of RAM.
And the storage requirements are even more indicative of the workload. It requires 3 distinct storage volumes.
Let me guess, they aren't small.
No, they are not. A primary 512 gigabyte SSD for the OS and application, a secondary 512 gigabyte SSD, and a third dedicated 512 gigabyte SSD specifically for the SEC artifact service.
Wait, hold on. Why do you need 3 separate half-terabyte solid-state drives just to run management software? What is happening on those disks?
It really comes down to IOPS input-output operations per second.
Okay.
The documentation explicitly states that the secondary drive must be an SSD provision for the RUCSEF storage class.
RUCSEF, what is that?
RUCSEF is a highly distributed, resilient storage system designed for cloud-native environments. See, when you're managing a massive pod, your database isn't just reading data. It is writing a staggering amount of time series telemetry constantly.
Right. If you have 10,000 temperature sensors recording in every single second, that is a massive write load on the database.
Exactly. If all of that telemetry, plus the application logs, plus the firmware artifact repository, we're all trying to read and write to the same physical disk spindle or even the same flash controller, the disk queues would just fill up.
The IOPS would max out.
Yeah, and when the storage under a management plane freezes, the entire dashboard hangs. You lose complete visibility into the data center.
That's a nightmare scenario.
It is. So by forcing the architecture to isolate the RUCSEF storage class onto a dedicated SSD,
Right.
SEC ensures that the high IOPS telemetry ingestion never starve the core application of disk access.
That makes perfect sense. You have to physically separate the logging I/O from the application I/O.
Exactly.
But even with 80 gigs of RAM and dedicated RICSF SSDs, a single master node VM has its limits.
Yeah.
How does SCC scale physically as a facility grows from like one aisle to a massive warehouse?
The sizing guidance chart details a linear scale-out architecture using what they call worker nodes.
Worker nodes.
In a non-high availability setup, you start with one master node and one worker node. This is the minimal configuration.
And the chart shows that this minimal mode manages up to 15 racks, which honestly sounds a bit low for enterprise software.
But you have to look at the footnote on that chart. Those numbers are evaluated based on what Supermicro calls a low-density rack configuration.
And what do they consider low density?
The text explicitly defines a low-density rack as a single rack consisting of just 3 GPU nodes.
Wait, 3 GPU nodes? That constitutes an entire rack.
Yes.
That alone tells you how massive and power-hungry these specific nodes are. I mean, in the old days, you could pack 41U servers into a single rack. Now, 3 GPU nodes max out the rack's power or thermal envelope.
That's wild, right?
We will definitely get into the physics of that shortly. But okay, so minimal is 15 of these ultra-dense racks.
Right, and if your facility grows, you step up to tiny mode by adding another worker node, bringing the capacity up to 45 managed racks. For standard mode, you deploy 1 master and 2 worker nodes, allowing you to manage 75 racks.
Okay, I see the pattern.
The documentation provides a very clear rule of thumb. Adding 1 worker node provides support for an additional 30 racks.
So the management plane itself is disaggregated. The master node handles the web interface and the orchestration logic, and it delegates the heavy lifting of direct API polling to the worker nodes.
Precisely. It distributes the processing load, and the manual notes that if your operations expand beyond 75 racks, scaling all the way past 150 racks into what they call advanced mode, you kind of cross a threshold.
What happens then?
At that massive scale, the documentation strongly advises consulting the SEC team directly for custom tuning. You can't just keep blindly adding worker nodes, because the network traffic generated just by the management telemetry can actually start to impact your production bandwidth.
Oh, wow.
Yeah, it requires bespoke architecture.
Okay, so we have built our data center, we have isolated our resources into composable pools, and we have deployed an array of master and worker nodes to monitor the pod without bottlenecking the storage IOPS. We have the foundation. Now we have to look at the payload. What are we actually running on this infrastructure in 2026? Section 3 of our outline dives into the generative AI highlights of release 3.1.0 because the priority of this release is undeniably clear.
Oh, it is entirely focused on large language models and AI supercomputing. The days of standard web hosting or monolithic SQL databases being the primary drivers of data center evolution are basically behind us.
Yeah, everything is AI now.
The very first module highlighted in the 3.1.0 update is the AI SuperCluster.
The AI SuperCluster. That sounds a bit like marketing jargon, but the text treats it as a very specific operational module. What does this actually do?
To understand its value, you really have to look at the history of high-performance computing.
Mm-hmm.
Historically, building a supercomputer was an artisan, sort of bespoke process.
Very custom.
Right. You had teams of PhDs designing custom interconnects, writing specialized MPI libraries, and spending months tuning the fabric just to get the nodes to talk to each other efficiently. You couldn't just buy a supercomputer. You had to engineer it from bare metal up.
But the SEC manual describes the AI SuperCluster module as a full turnkey data center solution. It claims to accelerate the time to delivery for mission-critical enterprise use cases and completely eliminate the complexities of large cluster design.
Exactly. It is the democratization of supercomputing orchestration.
Okay.
SEC abstracts that artisan complexity. The AI supercluster module allows administrators to manage in-rack CDUs, NVLink switches, power shelves, and compute trays, all from a single interface. It uses software to treat hundreds of discrete, disaggregated GPUs as one single, cohesive, massive brain.
And the hardware driving this brain is astonishing. The release notes explicitly list support for the GB200 and GB300 devices.
NVIDIA's Grace Blackwell architectures.
Yeah.
In 2026, these are arguably the most powerful, most dense, and most thermally intense AI accelerators in production.
The text mentions managing the GB300 power shelf, and it even coordinates firmware updates from varied vendors like Delta, Supermicro, and Lite-On simultaneously. It also explicitly mentions support for the GB200 NVL4.
Right, the NVL4 refers to a specific, highly dense, multi-GPU configuration tied together by NVLink. And that brings up a crucial operational challenge.
What's that?
Well, when you have a workload, say, training a massive multimodal large language model running across an NVL4 supercluster, the communication between those GPUs is happening at terabytes per second over the NVLink switches.
That's a lot of data.
If a single link degrades, the entire training run can stall.
Which is why the release notes highlight that SCC now supports event logs specifically for GB200 and GB300 devices. It pulls compute event logs, NVLink event logs, and something ominous called NVLink switch leak logs.
That word leak is our first real hint at the physical realities of cooling these chips, which we'll cover in depth.
Yeah, that word definitely caught my eye.
But before we get to the cooling, we have to look at the telemetry.
Yeah.
If you are a data center operative running a $100 million training job, you cannot afford to fly blind.
No.
SEC introduces a deeply integrated performance metrics module to provide absolute visibility.
The text says this module exposes a rich Grafana-like customizable analytics dashboard. For context, Grafana is an open-source analytics and interactive visualization web application. It's basically the industry gold standard for time series data.
Right.
SEC has essentially built this level of deep visual oversight natively into its platform for GPU workloads.
The granularity they expose is just incredible. The user can create customizable widget pulldowns to view GPU and storage metric metadata in almost real time.
So you aren't forced into a single view.
No, not at all.
Mm-hmm.
You can visualize the telemetry as a time series line chart to see trends over time, a min-max average sampling table for quick operational balance checking, a gauge meter for instant visual feedback on limits, or just a raw data table for deep debugging.
And you can scope this data dynamically. Like you can look at the macro level of the entire AI supercluster appliance, or you can drill all the way down to a single GB200 chip on a specific drawer in a specific rack.
That's right.
What specific metrics are they actually pulling from these chips?
The documentation highlights 3 critical indicators. You've got GPU unit power draw measured in watts, GPU unit SM clock frequency measured in megahertz, and GPU unit temperature measured in degrees Celsius.
Imagine sitting at the command center. A massive natural language prompt is submitted by an enterprise client.
Okay.
You can literally watch the dashboard as the SM clock frequency spikes. immediately followed by the power draw skyrocketing as the GPU pulls wattage to process the math.
And then seconds later,
The temperature curve bends upward as that electrical energy is converted into heat.
it is a perfect visual representation of the laws of thermodynamics in action.
It really is.
But it's not just about passively watching lines on a graph. The Monitoring Details module includes an analytics engine that collects historical data. It actually performs predictive analytics.
So it's not just reporting that a chip is hot. SEC can look at the derivative of the temperature curve, like how fast the heat is rising, and predict, based on this trajectory, GPU number 42 is going to cross its thermal threshold in 12 minutes.
Exactly. And it triggers accurate alert notifications long before the hardware actually suffers thermal throttling.
But there is a massive data problem here. If you have 10,000 GPUs generating power, clock, and temperature telemetry every single second, where does all that log data go?
Right.
We talked earlier about the dedicated Rook-Ceph SSDs for the master node, but surely months of historical telemetry for predictive analytics would overwhelm a 512 gigabyte drive in days.
It absolutely would. That's why SEC integrates with an external high-availability ELK cluster for massive deployments.
ELK cluster. Let's break that down for the architecture. What is that?
Sure. ELK is an acronym for a powerful stack of open-source tools: Elasticsearch, Logstash, and Kibana.
Okay.
It is designed to search, analyze, and visualize massive volumes of log data. Elasticsearch is the distributed search engine. Logstash is the data processing pipeline that ingests the telemetry. And Kibana is the visualization layer.
Ah, I see.
The manual specifically mentions utilizing the Logstash repository for historical trending and troubleshooting.
So SEC is intelligent enough to know what it shouldn't handle.
Exactly.
It acts as the orchestrator, pulling the real-time telemetry via the Redfish API, displaying the immediate Grafana-like metrics, but then it offloads the heavy, long-term data warehousing to a dedicated high-availability ELK cluster.
Precisely. By offloading the historical analytics, SEC ensures that the core orchestration engine never bogs down, even when the facility is generating terabytes of log data every single week.
That's super smart. So if you are running these massive generative AI workloads, SEC gives you unparalleled visibility. But looking at these performance metrics, specifically the power draw and the temperature, brings us to the most urgent crisis in modern infrastructure.
The heat.
Yes, the heat. These GB200 and GB300 chips pull an obscene amount of electricity. The manual even highlights a feature: support power capping for the B200.
Yeah, the fact that power capping is a listed feature tells you everything you need to know.
Right.
You literally have to put a software governor on the chip to prevent it from pulling so much current that it trips the breaker for the entire rack.
You have a single rack drawing hundreds of kilowatts. All of that electrical energy used to perform the AI calculations is ultimately converted into heat. And that leads us to section 4, beating the heat. The liquid cooling revolution.
The really fun part.
Right. How do we keep this density of compute from melting the building down to the foundation?
Well, that is the defining engineering challenge of 2026. Traditional air conditioning, the old method of pumping freezing air under a raised floor and using fans to blow it through the server chassis.
Right, the CRAC units.
Yeah, that is completely hopelessly obsolete for AI superclusters. Air simply does not have the thermal mass or specific heat capacity to carry that much energy away fast enough. The physics dictate a transition to liquid cooling.
And when you open the Cooling Infrastructure Info Center in SEC 3.1.0, it feels less like IT management and more like industrial plumbing.
It really does.
It outlines 5 distinct submodules to manage this liquid revolution: in-rack CDU, in-row CDU, sidecar, RDHX, and cooling tower. Let's trace a watt of heat from the processor all the way out to the atmosphere, starting inside the cabinet.
Okay, the heart of the rack level system is the CDU, the coolant distribution unit. The in-rack CDU module manages the units that sit directly inside the server cabinet, pumping fluid over the cold plates attached to the GPUs.
Okay.
The release notes highlight support for 100 kilowatt, EIA 250 kilowatt, and OCP 250 kilowatt in-rack CDUs.
I want to pause on that number.
Yeah.
250 kilowatts of heat rejection happening inside a single rack footprint. A typical home oven uses about 3 kilowatts when it's baking.
Right.
We are talking about extracting the heat equivalent of over 80 ovens, all running on high, packed into a space the size of a kitchen refrigerator.
It requires an incredible volume of engineered coolant moving at extremely high pressures, and this is where operations get kind of terrifying.
I can imagine.
You are introducing pressurized liquids directly adjacent to motherboards, carrying massive electrical currents. A leak is catastrophic.
Just a spark waiting to happen.
Exactly. So, SEC's monitoring has to be flawless. It collects vital real-time sensor data from the CDU, health status, pump status, valve status, pressure, flow rate, and heat load.
But the manual also explicitly lists two environmental metrics, humidity and dew point.
Yes.
Why does a liquid cooling dashboard care about the ambient humidity in the room?
Think about what happens when you take a glass of ice water outside on a really humid summer day.
It sweats. Condensation forms on the outside of the glass.
Exactly. The exact same physics apply in a data center. If the chilled liquid coolant coming into the rack is colder than the dew point of the ambient air in the hot aisle, moisture from the air will condense directly onto the cooling pipes.
Oh, no.
It will literally start raining inside the server rack. Water will drip onto the NVLink switches and the GPUs, causing immediate, catastrophic short circuits.
That is horrifying. So how does SEC prevent a multi-million-dollar rainstorm?
Well, by constantly monitoring the ambient humidity and calculating the dew point, SEC can dynamically interface with the facility water loop.
Okay, so it adjusts the water temperature.
Exactly. If the dew point rises, SEC can signal the mixing valves to slightly raise the temperature of the coolant entering the rack. It maintains the coolant temperature just a few degrees above the dew point threshold at all times, preventing condensation while still maximizing heat extraction. It is a constant, automated balancing act.
That is brilliant engineering. Okay, so that's the in-rack CDU managing a single cabinet. But an AI supercluster isn't one rack, it's dozens. When you scale up, you step up to the in-row CDU.
Yes, the in-row CDU is a massive piece of infrastructure. The document provides a visual example of a specific unit, the LCS SCDU 1K3LR001.
Yeah, I saw that schematic. It looks like a giant industrial transformer with a touchscreen interface on the front.
Its scale is immense. That specific unit has a cooling capacity of 1.3 megawatts.
1.3 megawatts. That's enough power to run a small residential neighborhood, and it is dedicated purely to moving heat.
The diagram shows this single behemoth unit connected to a massive 10-rack row of 42U racks. It acts as the central pumping station, distributing precisely chilled coolant to all 10 racks simultaneously.
And where does that heat go?
On its primary side, it interfaces directly with the outdoor facility water setup. And SEC monitors this 1.3 megawatt system with the exact same granularity it uses for a single GPU node.
That is so impressive. Next in the cooling arsenal is the sidecar module. The text describes a sidecar as a dedicated liquid cooling solution housed in a separate cabinet that physically bolts onto the side of the server racks it's cooling.
Right.
It mentions two main configurations, liquid-to-air, LTA, and liquid-to-liquid, LTL.
These serve very different facility architectures. A liquid-to-liquid sidecar is the most efficient. It transfers the heat from the rack's internal closed coolant loop directly into the building's main facility water loop via a heat exchanger.
That makes sense.
But what if you were retrofitting an older data center that doesn't have a massive chilled facility water loop piped to the data floor?
Then you use liquid-to-air.
Correct. An LTA sidecar uses liquid in a closed loop to pull the intense heat directly off the GB200 chips.
Okay.
But instead of passing that heat to a facility water loop, it pumps the hot liquid into a massive radiator inside the sidecar and uses high-velocity fans to blow that heat out into the ambient room air where the traditional CRAC air conditioning units can deal with it.
So it's basically a bridge technology for legacy facilities.
Exactly.
But whether it's LTA or LTL, SCC is constantly monitoring the health of these sidecars. And one of the metrics it tracks is completely fascinating to me: turbidity.
Turbidity is a critical health indicator for liquid systems.
For those who aren't chemical engineers, turbidity is basically the cloudiness or haziness of a fluid caused by large numbers of individual particles that are generally invisible to the naked eye. Why does SCC care if the water is slightly cloudy?
Because of the microchannels.
Microchannel?
Yeah, the cold plates that sit directly on top of the GPUs have incredibly tiny microscopic channels machined into them to maximize surface area for heat transfer. If the coolant starts getting turbid, if it gets cloudy, it means particulate matter is accumulating in the loop.
What causes the particulate? Like, where does it come from?
It could be a few things. Galvanic corrosion between different metals in the loop, or the breakdown of the coolant fluid itself, or even biological growth like algae if the biocide levels drop. Or perhaps a micron filter is ruptured.
And if you don't catch that cloudiness early,
that particulate matter will flow directly into the microchannels of the GPU cold plate and clog them.
And then
the coolant flow stops. Within seconds, a $50,000 GPU overheats and destroys itself.
Wow.
We're talking about preventing microscopic blockages from taking down massive AI training runs. That's why SEC tracks turbidity alongside flow rate and pump pressure.
So it's an early warning system.
Exactly. If turbidity spikes, SEC can trigger an automated alert to swap the filters or flush the loop long before a thermal event occurs.
The level of granular physics involved here is just staggering. Okay, the fourth cooling technology is the RDHX, the rear door heat exchanger. I am obsessed with this concept because it solves the heat problem at the exact point of exit.
The manual describes it beautifully. It is a high-efficiency cooling device that literally replaces the standard rear metal door of a server rack.
Right. Imagine the back door of your server cabinet is actually a massive, high-tech, liquid-filled radiator. As the servers blow their hot exhaust air out the back, instead of that heat escaping into the hot aisle and overwhelming the room's AC, the hot air is forced directly through this radiator.
Right. And the text notes that these RDHX units have a 50 kilowatt nominal cooling capability per rack. The engineering relies on chilled water circulated through dense coils.
Okay.
The superheated air from the servers passes through the coils, deposits its thermal energy into the water, and exits the door into the data center room at a completely neutralized normal temperature.
It's like putting a customized high-performance air conditioning unit directly over the tailpipe of a sports car. The heat never even makes it into the room.
That's a perfect way to picture it.
Yeah.
And SEC's management of these doors is highly sophisticated. The text highlights that the RDHX units feature hot swappable ECE fans. EC stands for electronically commutated. They are highly efficient brushless DC motors that allow for precise variable speed control.
And hot swappable means if one of the fans in the door dies, a technician can just pop the housing out and slide a new fan in while the system is still actively running.
Exactly.
The documentation specifically mentions redundant fans features with zero downtime during service. The airflow never stops.
But the true intelligence really lies in the control logic. The manual mentions temperature and differential pressure-based control modes.
What does that mean in practice?
Well, SEC isn't just running these fans at 100% all the time. It uses sensors to read the air pressure on the inside of the rack door versus the ambient pressure in the room. It then dynamically speeds up or slows down the EC fans to ensure the exhaust air moves through the radiator coils at the exact perfect velocity for maximum heat transfer, matching the CFM cubic feet per minute output of the servers themselves.
That is just so cool. And the final piece of this massive thermal puzzle is the cooling tower module. This is the end of the line. The heat has been pulled off the GB200 chips by the cold plates, moved to the CDUs, transferred to the facility water loop, and now it gets pumped all the way up to the roof of the data center,
where SEC monitors the massive cooling towers evaporating that heat out into the outside atmosphere.
It's a complete cycle.
It is. By tying all of this telemetry from the microscopic turbidity in a sidecar loop to the macro heat rejection of a megawatt cooling tower into a single unified dashboard, SEC allows operators to dramatically reduce their total cost of ownership.
Because they're only cooling exactly as much as needed.
Right. You aren't wasting electricity overcooling the room, and you aren't suffering catastrophic hardware failures due to condensation or microchannel clogs.
So, we have the massive, disaggregated AI compute power. We are successfully keeping the silicon from melting using megawatts of precision-controlled liquid cooling. But none of this works, especially in a composable disaggregated infrastructure, if the disparate pieces can't talk to each other instantly.
That's the glue.
Exactly. Which brings us to Section 5, the nervous system, networking, and topology.
Right. As we discussed earlier, disaggregation places an immense, almost impossible burden on the network fabric.
Yeah.
If a CPU in rack A is dynamically paired with an NVMe flash drive in rack B, the network between them must operate with practically zero latency.
Otherwise.
If the network stutters, the CPU is left waiting for data. The compute cycle is wasted, and we are right back to our inefficient factory spinning its wheels.
The manual spends a lot of time on the network module, explaining how SCC constructs VLANs, virtual local area networks. It says it uses these VLANs to partition specific workloads from segmented broadcast domain traffic.
Yes.
Why is partitioning so critical in a pod of this scale?
Well, a broadcast domain is a logical division of a computer network. When a device on the network needs to find another device, it often sends out a broadcast packet, a message, that goes to every single connected node asking, who has this IP address?
Okay, imagine a room with 10,000 people in it, and everyone who needs to find someone has to yell their name at the top of their lung.
Exactly. The noise floor becomes deafening. If every single node in a 150-rack AI supercluster received every single broadcast message, the network's switch CPUs would choke just processing the noise.
It would just crash.
The data center would collapse under its own chatter.
Yeah.
By automatically partitioning workloads into tightly isolated VLANs, SCC ensures that the storage traffic for one tenant's AI model is completely invisible to the compute traffic of another tenant. The broadcast domains are segmented and silenced.
But I've talked to network engineers. Configuring complex, overlapping VLANs across hundreds of Arista or Mellanox switches used to be an absolute nightmare.
Oh, it's terrible.
You'd have a senior engineer sitting in a terminal window, typing CLI commands for hours, hoping they didn't mistype a subnet mask.
Which is where human error introduces massive outages. SEC 3.15R0 tackles this with the network provisioning feature. It entirely abstracts the command line.
The text details a network configurator wizard. It's a GUI-based wizard that allows the architect to visually design the network requirements. SCC then translates that visual design into build plans using JSON format.
JSON JavaScript object notation is a lightweight data interchange format. It's highly structured and machine-readable.
So instead of manually typing configurations switch by switch, you design the entire highway system in the wizard. You verify the design, you hit a button, and the manual says the network orchestrator engine pushes these JSON plans out as multi-thread operations. It configures multiple switches simultaneously.
It acts like an automated city planner. It paves the roads, sets up the traffic lights, and routes the lanes across the entire fabric in seconds, using the standardized API calls we discussed earlier.
It's so much safer.
Right. It removes the human latency and the typographical errors from switch configuration.
But I hear automated network orchestration across multiple switches, and my first thought as an engineer is, great, now instead of misconfiguring one switch by accident, SCC can misconfigure 100 switches simultaneously.
Well, that's a valid fear.
How does an operator actually verify the health of this automated mesh? When a cable goes bad or an optics module fails, how do you find a single degraded link in a network of 100,000 connections?
You use the topology module. The documentation describes it as an infrastructure visualization tool where connected entities of links and nodes are intersected together, representing networks.
There is a screenshot in the manual showing what they call the hop view. It looks like a complex constellation of stars. You have a central spine switch in the middle and hundreds of dashed lines connecting out to various leaf switches and end nodes, all color-coded for their real-time health status.
The hop view is brilliant for rapid diagnostics. In networking, a hop is one segment of a path between routers or switches. If an AI training job suddenly reports high storage latency, the operator doesn't have to guess where the bottleneck is. They can click on the affected compute node in the topology view and instantly trace every single physical and logical hop between that node and the JBOF storage.
And because it's actively polling the API, SCC visually highlights the exact link that is dropping packets or experiencing errors.
Exactly.
You can see the exact degraded SF module in a meshed framework instantly.
But diagnosing the physical links is only half the battle. We have to talk about the protocol level. We mentioned earlier that this network has to be fast enough to make disaggregation feel like local hardware.
Right.
The glossary at the back of the manual defines two technologies that make this microsecond latency possible: RDMA and RoCE.
Let's unpack RDMA first, remote direct memory access.
To truly grasp why RDMA is revolutionary, we have to look at the inefficiency of the standard networking model.
How does it normally work?
Normally, if computer A wants to read a block of data from computer B's memory over a network, a massive chain of events occurs. Computer A's application asks its operating system kernel for the data. The OS kernel copies the request to the network interface card, the NIC. The NIC sends the packets across the wire.
And then the reverse happens on the other side.
Right. Computer B's NIC receives the packets. It fires a hardware interrupt to tell Computer B's CPU to stop what it's doing. Computer B's OS kernel takes over, reads the network buffer, copies the data out of system RAM, packages it back up, and sends it all the way back down the chain.
Every single one of those steps involves the CPU context switching and the operating system kernel getting involved. It burns CPU cycles just moving data, and it adds massive latency.
The glossary defines RDMA as permitting direct memory reads from memory of one computer into another without an operating system.
Oh, wow.
It is a literal hardware bypass. With RDMA, Computer A's network card talks directly, physically, over the PCIe bus to Computer B's memory RAM. The operating system is completely bypassed. The CPU on both ends doesn't even know the transfer happened.
It just silently reaches across the network and pulls the data out of RAM. The latency drops from milliseconds down to single-digit microseconds.
And that leads us to ROCE, R-O-C-E.
Which stands for RDMA over Converged Ethernet.
Historically, achieving that magical OS bypassing memory access required highly specialized proprietary networking fabrics like InfiniBand. It was incredibly expensive.
So what does ROCE do differently?
ROCE does is encapsulate those RDMA commands so they can travel over standard, ubiquitous Ethernet networks.
The glossary explicitly notes ROCE is one of the possible foundations of NVMe-OF, the NVMe over Fabrics protocol that connects our compute to our JBOF.
Without ROCE bypassing the operating system, the overhead of moving terabytes of data across the network would choke the CPUs, and true composable disaggregated infrastructure would be physically impossible.
It is the unseen protocol that makes the entire SuperCloud Composer ecosystem viable.
Absolutely.
Okay, we are entering Section 6, the final phase of our deep dive. We have the raw composable compute, we are aggressively cooling it with liquid heat exchangers, and the RDMA network is moving data at the speed of thought. Finally, we need to talk about keeping the lights on. Power, firmware, and governance. The administrative backbone.
It might seem like the least glamorous part of running a data center, but administrative governance is the layer that keeps you from ending up on the front page of the Wall Street Journal for a catastrophic global outage.
Too true. Let's start with power delivery. The PDU console module. A PDU is a power distribution unit.
Right.
In a standard data center, these run vertically down the back of the rack and supply the actual electricity to the server power supplies. The 3.1 of release notes highlight support for a suite of new Schneider APC ePDU models. And it specifically mentions managing cascading modes. What does cascading mean in this context?
Every smart PDU requires an IP address on the management network so SCC can talk to it. But if you have 50 racks, each with 4 PDUs, that is 200 IP addresses and switch ports consumed just for power strip.
Oh, that's wasteful.
Cascading allows an engineer to connect multiple PDUs together in a physical daisy chain.
So they share a single network uplink and a single IP address for management.
Exactly. It vastly simplifies the network topology and saves expensive switch ports. Through that single IP, SCC can manage the entire cascaded chain. It can monitor the load across different electrical phases, the specific breaker banks, and even down to the individual outlets.
Why do you need outlet-level control from a software dashboard?
Imagine a bare metal compute node completely locks up. The OS is frozen, the out-of-band management controller is unresponsive. A technician can't SS into it.
It's completely dead to the network.
Instead of sending a human being walking down a hot aisle at 3 a.m. to physically pull the plug, an administrator can use SCC to remotely cut the power to that exact specific outlet on the PDU, wait 10 seconds, and turn it back on, forcing a hardware reboot.
The power of remote administration, which leads perfectly into the artifacts and logs modules. Artifacts, in this software context, primarily refers to firmware bundles.
Yes.
The manual details how SCC acts as the central repository for switch firmware and complex supercluster firmware, like updates for the compute tray, the power shelf, and the BMC, the baseboard management controller.
Updating firmware on a tightly coupled AI cluster is terrifying. It is a house of cards.
Tell me about it.
If you push an update to the Mellanox switches, but that firmware version isn't perfectly compatible with the exact firmware running on the GB200 GPUs, the NVLink fabric crashes. The whole cluster drops offline.
So SCC manages this lifecycle to ensure compatibility. The release notes even mention a new automated feature, configuration baseline management for the BMC, BIOS, and RAID setups.
Baseline management is crucial for drift prevention.
Drift prevention.
SCC knows exactly what the gold standard perfect configuration should look like for every node. If a server drifts from that baseline, say, a junior admin logs into a specific node and accidentally disables hyperthreading in the BIOS or changes a RAID stripe size.
Oh, I've seen that happen.
Right? SCC immediately detects that the node no longer matches the baseline. It can flag it for review or automatically remediate it by pushing the correct configuration back down.
It forces compliance. And when things do inexplicably fail, you rely on the logs module. A log is simply a machine-generated record of an event. The text states that SCC provides 3 distinct levels of log collection: component level, server level, and rack level.
This hierarchical logging is vital for root cause analysis. You can zoom all the way out to the rack level to see that rack 14 experienced the sudden voltage drop.
Okay.
Then you zoom into the server level to see that Node A initiated a thermal shutdown. Then you zoom all the way down to the component level to see that EC fan number 3 in the rear door heat exchanger reported a rotor lock failure milliseconds before the thermal event.
You can reconstruct the exact timeline of the failure. And the manual mentions that these logs are strictly maintained to enforce governance, compliance reporting, and general serviceability.
Which brings up the most critical vulnerability in any automated system, the human operator.
Exactly my final question. We are looking at the admin module, and the release notes mention features like OBOS multiple deploy.
Right.
OOB meaning out of band. It means SEC can bypass the installed operating system, talk directly to the bare metal hardware via the BMC, and deploy a fresh image of Rocky Linux 9.6 or Ubuntu 24.04 across 5,000 machines simultaneously.
It is an incredible amount of power to hand to an administrator.
Too much power. With the ability to wipe operating systems across a pod, cut power to entire racks via the PDU console, and push experimental firmware. How do we prevent a well-meaning but inexperienced junior technician from making one wrong click in the GUI and taking down a $100 million AI training job?
It all comes down to the admin module's primary governance function, role-based access control, or RBAC.
Okay.
The manual states unequivocally that accountability, governance, and compliance are paramount. In SEC, a user doesn't just get an account. When the global admin creates a profile, they must assign a predefined, strictly limited user role.
So you segment the humans just like you segment the VLANs.
Precisely. Each role is mathematically defined by the exact API endpoints and tasks they are allowed to execute.
Can you give an example?
A technician assigned a viewer role might be able to log in and see the beautiful hop view topology map to check network health. But the RBAC system literally removes the buttons in the GUI that would allow them to push a new JSON network configuration. The system simply won't accept the command.
So the network engineer can't accidentally reboot the cooling towers, and the facilities manager can't accidentally wipe the storage arrays.
Right. The release notes also highlight deep security upgrades under the hood to support this governance. It mentions a critical requirement to upgrade OpenSSL to 3.5.2 or later, ensuring that all API traffic and user sessions are encrypted against modern cryptographic standards.
And what about logging who did what?
It mentions Phase 1 updates to the BMC host name functionality to ensure precise audit logging of exactly that, who touched what and when.
Combined with what the text calls the support advisor and strict enforcement policies, SCC ensures that operatives only touch what their role explicitly allows. It builds a walled garden to maintain stability in a highly fluid, highly automated environment.
It has to, right?
So when we step back and look at the totality of what we've discussed, what does this all mean for the future of infrastructure?
Well, I think
Actually, let's synthesize the journey we just took. The SuperCloud Composer 3.12.0 release is not just a software update with a few bug fixes and a UI refresh. It is the operating system for a completely new kind of physical entity.
yes.
It is the central nervous system of a disaggregated megawatt liquid-cooled AI-optimized megacomputer.
That is exactly the right perspective. Whether an engineer is managing a small 2-rack edge deployment or a massive multi-megawatt enterprise cloud, understanding this composable framework and the physics of the cooling and networking that support it is the absolute key to surviving the next decade of IT infrastructure.
The old way is dead.
The days of racking a static, inefficient server box and hoping for the best are over. The sheer physics of generative AI demand disaggregation and liquid cooling.
And SCC is the tool that makes that extreme physics manageable for human operators. But before we sign off, based on everything we've decoded from this manual, do you have a final thought on where all this automation and telemetry is ultimately heading?
I do, and it builds on the predictive analytics we discussed in Section 3. Consider this trajectory. Today, SCC allows humans to use software to perfectly compose, provision, and dynamically cool hardware on the fly.
Right.
But we just discussed how these massive AI superclusters are already running predictive analytics on their own telemetry, offloading that data into high-availability ELK clusters to spot trends humans can't see.
Right, predicting a thermal event before it happens.
Now take that one step further. As the large language models running on these clusters grow exponentially smarter, and as they are fed the real-time operational telemetry of their own physical hardware,
Oh, I see where this is going.
how long until the data center realizes it can optimize itself?
Wow.
How long until the AI analyzes its own workload, predicts a massive compute spike, automatically provisions 50 more disaggregated GPUs from the JBOF pools, ramps up the in-row CDU liquid cooling flow, and repaths the RDMA network fabric to avoid a microsecond bottleneck? all without a human being ever logging into the dashboard.
That is both incredible and slightly terrifying. It completely changes the definition of an autonomous system. We aren't just talking about self-driving cars, we're talking about self-architecting, self-healing computational warehouses.
The physical infrastructure will become a living, reacting organism.
It takes us right back to our opening metaphor. We started by imagining a factory full of spinning, useless machines burning electricity.
Yep.
With SuperCloud Composer, every machine is utilized, every ounce of power is directed with absolute purpose, and the factory floor runs with fluid, orchestrated efficiency. And based on where the telemetry is heading, very soon, the factory will be running itself.
It's just a matter of time.
Thank you so much for joining us on this deep dive. We hope this blueprint helps you understand the intense physical reality powering the cloud today. Until next time, keep questioning, keep learning, and we'll see you in the next one.